Hey Maximum. Getting pumped?
Howdy Optima. Yeah, I want my buddies to call me the Big M.
You crack me up. I will call you the Big M if you help me prepare a quiz on the Big M method.
Deal? But can we go over an example first?
Sure thing. Let's start with an example of the two-phase simplex method.
Sounds good. We need to warm up for the Big M.
Right. We start by setting up the auxiliary problem.
So, we convert the constraints to the standard form and introduce an artificial variable for each constraint where it is needed.
Recall that converting the constraints to the standard form means that all the inequalities need to be transformed into equalities by adding a slack variable, or subtracting an excess variable, depending on the type of a constraint.
For the equality constraints we don't need to add or subtract anything. This is nice, but then there is no obvious starting basic variable to use for such a constraint, because it doesn't have a slack or excess.
That's right, so we will have to add an artificial variable for every equality constraint, to make sure we have a starting basic variable.
We may also need artificial variables for some of the inequality constraints, right?
Yes, if a less than or equal to constraint has a negative right-hand side, then the slack variable will be negative if we set the rest of the variables to 0 in that constraint, so it cannot be a part of the initial basis and we need to introduce an artificial variable.
Same thing with a positive right-hand side in a greater than or equal to constraint, correct?
Yes. This covers all the cases for the constraints.
How about the objective?
The objective of the auxiliary problem is to minimize the sum of all the artificial variables.
We want to drive them all down to 0, to make sure we can get rid of them.
Right, use them then lose them.
Makes sense.
Once we set up the auxiliary problem, we proceed to phase 1.
So, phase 1 determines if the original LP is feasible or not.
Precisely. We solve the auxiliary LP using the simplex method. There are two possibilities. The optimal objective value of the auxiliary problem is either 0 or not 0.
So, if it is 0 then the original LP is feasible. We tell the artificial variables to get lost and proceed to phase 2.
Yes. And if the optimal value of the auxiliary problem is not 0, we don't need to assault the artificial variables.
We thank the artificial variables for their help and report that the original LP is infeasible. Brilliant?
Yes, I bet the students will like this second possibility more than the first one.
Of course, less work and no reason to be rude with the artificial variables.
Nevertheless, all practically reasonable models will be feasible, so we have to proceed to phase 2.
Fine, phase 2 it is.
Once again, phase 2 is performed only if the LP was found to be feasible in phase 1. Since the LP is feasible, it is either optimal or unbounded.
And the second phase reports an optimal solution in the LP is optimal or concludes unboundedness otherwise.
Correct. So, we start setting up the phase 2 tableau by removing the artificial variable columns from the optimal tableau of the auxiliary problem. Then we replace row 0 of the resulting tableau with the objective of the original LP.
After that we eliminate all non-zero basic variable coefficients in row 0.
And finally, we solve the phase 2 LP using the simplex method.
The simplex will lead us to either an optimal solution or to the conclusion that the LP is unbounded.
Great, let's check out a numerical example.
It is about the time. We have this LP for which the auxiliary problem was already formulated in the previous video.
We have two artificial variables because in the first two constraints the excess variable and the right-hand side had different signs.
Indeed, we cannot use E1 as the basic variable for the first constraint, because if we did, we would have E1 equal to -12 in the corresponding solution.
The basic solution that has E1, E2 and S3 as basic variables is infeasible.
And we resolve this by introducing the artificial variables A1 and A2 for the first two constraints.
The goal of phase 1 is just to find a feasible solution, no matter how bad it is. We forget about the original objective for now and minimize the sum of all the artificial variables instead.
But the slide says maximize.
Maximizing the negative of the sum of all the artificial variables is the same as minimizing the same sum, so it's an equivalent problem.
I am all for using maximum, instead of minimum whenever we can, but why exactly do we switch to maximizing in this case?
Well, we don't have to, it's just the students are used to maximizing by now, because all the examples we considered so far were maximization. I prefer to switch to maximum to avoid confusion with the rule for picking the entering variable.
I guess you are right. Everyone in the class knows that we pick a variable with a negative coefficient in row 0 as the entering variable, and with minimization it would be the opposite.
Right, and this may be confusing and easy to mix up. Instead, I recommend the students to stick to maximization, and convert any minimization problem to maximization by multiplying the objective by -1.
I like this approach. But whoever uses it needs to keep in mind that in the end they need to reverse the sign of the optimal objective value to the opposite, because effectively they maximize negative z instead of minimizing z.
Obviously. Anyways, let's set up the initial tableau for phase 1.
That's easy. We've done this many times by now.
I can tell you do your homework.
Of course, we have to practice what we preach.
I agree, and I'll never get tired of reminding people about the importance of homework. You know, Thomas Edison said, "A genius is a talented person who does homework."
No wonder he is America's greatest inventor. I like another one of his quotes: "Opportunity is missed by most people because it is dressed in overalls and looks like work."
That's a good one. Let's not miss the opportunity and do some work.
Let's do it. Looking at this tableau, I don't know where to start.
How come?
Well, don't we need a negative entry in row 0 in order to select the entering variable?
Indeed. But what we have here is not the initial tableau yet.
How come? I set it up as I have always done before.
Okay, what are your basic variables?
A1, A2, and S3, obviously.
Precisely. And what are the coefficients for A1 and A2 in row 0?
Both of them have the coefficient equal to 1.
But since they are basic variables, don't their coefficients in Z row have to be 0?
You are right, only non-basic variables can have non-zero coefficients in Z row. So, to get the initial phase 1 tableau, we need to eliminate A1 and A2 from the objective.
Exactly.
Luckily, this is easy to do. We just need to subtract row 1 and row 2 from row 0.
Yes, this is exactly what we need to do.
Okay, so the coefficient for x1 is 2 minus 3, which is -1. The coefficient for x2 is -3 minus 2, which is -5. For x3 we have -4 minus 1, which is -5 again.
The coefficients for E1 and E2 are both equal to 1, for S3 it's 0.
Finally, we managed to eliminate the artificial variables from the objective.
Excellent. Now we have the initial phase 1 tableau.
And once it is set up, it is business as usual. Now we just need to apply the usual simplex iterations. We can see that the optimal objective value is 0, meaning that the original LP is feasible and we've got some more work to do here.
That's right. If the optimal objective value was negative, we would be done, because this would mean that the original LP is infeasible. But since we got 0, we have to proceed to phase 2.
What a great opportunity to practice more simplex iterations.
I like your enthusiasm, Maximum.
Of course, you have to love what you do, so that you do what you love.
Wow. That was deep.
Always happy to impress. It doesn't happen very often.
So, phase 2.
Right, because the optimal objective of the auxiliary problem was 0, we concluded that the original LP is feasible, so we are setting up the initial phase 2 tableau.
We drop the artificial columns and bring back the original objective function instead of the one used in phase 1.
The original objective was x1 minus 2x2 plus 3x3, so we move all the variables to the left and input the resulting coefficients in row 0.
Just like with starting phase 1, you need to eliminate the basic variables from the objective in order to obtain the correct initial tableau for phase 2.
But this time it is not as easy as in the first phase. Now I need to multiply the first row by 3, the second row by -2 and add both of the resulting rows to row 0.
That's an opportunity to practice your arithmetic skills.
Indeed. That never hurts. Unless there are too many fractions.
Once the initial tableau is set up, it is once again business as usual. We just proceed with the standard simplex steps to solve the LP.
So, after 3 iterations of the simplex method, we obtain the optimal solution for the second phase.
This solution is also optimal for the original LP.
We are done with the 2-phase example. Finally, it is the big M time.
Yes, but remember, with big M comes big responsibility.
You mean, lots of arithmetics. I know. I am up to the challenge and ready to pull my weight.
Let's do it then. We will use the same example as with the 2-phase method.
Wonderful, we already have the big M problem set up for us.
Yes, the constraints are exactly the same as in the auxiliary problem, but the objective is different. Instead of minimizing the artificial variables explicitly, we penalize them by subtracting them from the original objective with some big positive coefficient m. The big M coefficient makes sure that the artificial variables vanish whenever the original LP is feasible. Now, let's put our big M LP in the tableau format.
Done.
The big M method is very similar to the ordinary simplex method. Let's focus on what's unusual about the big M method compared to what we have done before.
I would prefer to use special instead of unusual.
Fine. The special part is the big M parameter appearing as the coefficient for all the artificial variables in row 0 of the tableau. This parameter is essentially treated as plus infinity.
What's important, it is bigger than any numerical value we encounter during the simplex iterations.
Precisely. This means that whenever we compare two coefficients involving the big M in row 0, the coefficient with a greater multiplier for the big M is considered greater than the other one.
Of course.
Other than dealing with the big M in row 0, all the simplex steps are the same as usual.
Yes, the big M is the difference maker.
Also, once we obtain an optimal tableau, we check whether all the artificial variables are equal to 0 in the corresponding optimal solution.
If they are, it's a good thing, right?
Yes, in this case the solution we obtained is also optimal for the original LP. And if at least one of the artificial variables is positive in the optimal solution to the big M problem, then the original LP is infeasible.
Makes sense. I'm ready to do the work now.
Okay. First, we need to get rid of the artificial variables in the objective in order to get an appropriate initial tableau. Remember, no basic variables in the objective.
Yes. Non-basic variables only. We need to multiply row 1 and row 2 by negative m and add both resulting rows to row 0 in order to get rid of the artificial variables in the objective.
Precisely. I'm sure all the students in the class know what needs to be done here by now.
I would assume so. If they don't, they better talk to us as soon as possible.
We obtain the following initial tableau.
And now it's business as usual again, right?
For the most part. Only row 0 computations will be unusual. I mean, special. I suggest we go over the details for at least one iteration.
Okay, let's do it. We see that there are 3 variables with negative coefficient in row 0, x1, x2, and x3. Even though both x2 and x3 have the multiplier of negative 5 for m, the coefficient for x3 is more negative, because it also has the negative 3 term, whereas x2 has plus 2 instead. So, we pick x3 as the entering variable.
Great. I just want to reiterate that in general we don't have to pick the variable with the most negative coefficient as the entering variable. Any negative coefficient will do.
Yes. We just decided to stick to the Danzig rule to be more specific with our choices, so we pick a variable with the most negative coefficient according to this rule.
Okay, let's choose the leading variable.
The ratio test in the big M method is exactly the same as in the regular simplex method.
Yes, the big M coefficients appear only in the objective and don't impact the minimum ratio test.
So, the first row is the winner, with the ratio of 3. The pivot element is shown in the square. Let me underline the winning row.
Next, you need to divide this row by the pivot element to update it.
Sure thing, this part is also business as usual. The new basic variable for this row will be x3, which replaces the first artificial variable in the basis.
Wonderful. Now, the special and tough part, updating row 0.
When the going gets tough, tough get going. Let's do it.
Go for it.
So, to eliminate x3 from row 0 I need to multiply my new row 1 by 5m plus 3 and add the result to the old row 0. Let me first do the multiplication. Now, I will copy the coefficients from the old row 0 here to minimize the chance of an arithmetic error. Looks like we are ready to add. It's going to be fun. One here as usual. Then negative 7m plus 5 over 2. Negative 5m minus 17 over 4. 0. Negative m plus 3 over 4. m, 0. 5m plus 3 over 4. 0. Finally, negative 3m plus 9. Okay, done. Optima, I am happy to introduce to you the result of my labor of love, our new Z row.
Okay, let me check if the numbers are correct.
You don't trust my arithmetic skills.
Trust, but verify.
Okay, the rest of the computations for this iteration of the Big M method are exactly the same as in the usual Simplex method, so I suggest we skip the details and let the students do it themselves as a homework.
Agreed. How about the next step?
In the next step, x1 is the entering variable because it has the most negative coefficient in row 0. The second row wins the ratio test, and then we proceed as before.
I see you are not eager to go over the details of computing the updated row 0.
You read me right? Don't get me wrong, I would love to do it, but we also need to give the students an opportunity to enjoy the process. I trust they know how to work this out by now.
Trust but verify.
We will have a quiz for that. But for now, let's just skip through the steps to the final optimal tableau.
Okay. After just 4 iterations we get the same optimal solution as we obtained using the two-phase simplex.
Not surprising, it is the same problem.
Right. Both artificial variables are equal to 0, that's why we can claim that the solution is optimal for the original LP.
And here is my message to the artificial variables.
Relax. You've been erased.
It is indeed a good time to take a break and relax before we proceed to the last part of this lecture.
Relax? No way. Would you care joining me for the next round of my amazing workout instead?
All right, the Big M. As long as you don't make me lift the weights.